Today I'd like to get you to rethink the basic concept of pulse sequences and how we acquire data at the MRI scanner. Almost all pulse sequences as we know them are static. Sequence parameters, topology and contrast remain the same for different subjects. Today I will present you with an adaptive framework for sequence design in which the sequence changes in real time in response to incoming data from the subjects inside the scanner. I'm going to describe a particular application of this to the measurement of the transverse T2 relaxation times of the N-acetyl aspartate molecule. However, the ideas I will lay out are completely general and can be applied to any sequence and any type of contrast. The conventional measurement of T2 uses a spin echo sequence. I'm going to make a few simplifying assumptions. We're going to acquire a single echo in each excitation and keep TR long enough to let the spins return to thermal equilibrium. By varying the echo time, we can acquire data points which lie ideally on an exponentially decaying curve. We then fit this curve with an exponential to extract T2. Before considering the adaptive case, let's look at the static case. The possible T2 values of NAA found in vivo have a wide range, from 50 milliseconds all the way up to 450 milliseconds. Without any a priori knowledge, we have to assume an equal uniform distribution of possibilities. Now, given this prior knowledge on T2, how should we choose our echo times to best estimate T2? One approach to solving this problem involves minimizing the Kramer-Rao lower bound. This is of course the Kramer-Rao bound average over all possible T2 values expected in the sample. If we assume we have a 2-minute acquisition with a TR of 6 seconds, meaning we have 20 acquisitions in total, and we minimize the Kramer-Rao bound, we find that our TEs need to be distributed between 40, 110, and 370 milliseconds at a 1:8:11 ratio. The problem with this approach, of course, is that it is only optimal in the average sense. I will now describe an adaptive framework for carrying out the same experiment. This framework operates by maintaining a distribution, quantifying our belief on the different values of T2. Initially, it is uniform between 50 and 450 milliseconds. However, it changes its shape throughout the experiment. Given such a distribution, we can calculate the assumed or believed average value of T2. We can use this value then to select our next echo time. There are different ways of doing this. The simplest one minimizes the Kramer-Rao bound for the problem. The difference now is that the Kramer-Rao bound is not an average one. It is the Kramer-Rao bound for the particular mean T2 that you've calculated from your prior. Minimizing such a bound yields a simple solution. You place your echo times at a 1:5 ratio between 0 and 1.4 times the assumed T2 value. You can choose your next echo time to make sure your distribution of echo times approximates this 1:5 ratio as best as possible. The choice of echo time is sent to the scanner and a new measurement is made. We can use this new data point to calculate what's known as a likelihood function. This expresses the probability of each possible value of T2 based on the new measurement. Because noise is normally distributed, this function is a Gaussian. Finally, the likelihood function is multiplied by the prior, renormalized, and used as the new prior. This is a straightforward application of Bayes' rule. Here, I show data collected from an adaptive acquisition in a phantom, where the framework was used to acquire the T2 relaxation time of choline. This is a 5-minute acquisition with a TR of 6 seconds and therefore collects a total of 50 echo times. The following movie therefore has 50 frames, each frame corresponding to a different excitation. First, you can see how the distribution of T2 varies as a function of time throughout the acquisition. This changes in real time. Next, you can see how the mean of this distribution changes as a function of time. As the adaptive loop is executed again and again, the estimate of the mean becomes better and better and converges to around its true value, denoted by the dashed black line. Finally, you can see how the adaptive algorithm spaces out the echo times. The adaptive framework converges very early on during the acquisition and approximates the true 1:5 distribution of echo times for the true T2 value of the sample. The adaptive framework was implemented on a Siemens scanner using the real-time ICE framework. 7 volunteers were scanned using a single voxel MRS acquisition placed in parietal white matter, and the T2 of NAA was quantified. Static and adaptive acquisitions were compared. The bar plots show the mean and standard deviation for both the adaptive and static acquisitions for each of the 7 volunteers. Each white dot is a separate single experiment lasting 2 minutes. First, note that both approaches are unbiased. There is no statistically significant difference between them. However, the standard deviation of the adaptive approach is smaller than that of the static approach by a factor of approximately 1.7. This is equivalent to an increase in SNR per unit time by a factor of 70% for adaptive acquisitions. This precision can be traded off for acceleration. By using the first 40% of echo times, the first 48 seconds of the adaptive acquisition, we can get the same precision as for the full 2-minute static acquisition. The adaptive framework can be applied to any acquisition that relies on some sort of signal model: diffusion, relaxation, chemical exchange, saturation transfer, and so on.